Hey everyone, welcome back to the channel. Today we are diving into one of the most important topics in the modern robotics, communication in ROS2. If you've ever wondered how robots make all their parts talk to each other, how controllers make decisions, and how planners coordinate everything, this video is for you. We will explore how ROS2 makes all that possible through its communication models. The publisher-subscriber model for continuous data exchange, the server-client model for on-demand request, and the action server-client model for handling long-running tasks. By the end of this lecture, you will not only understand how communication works in ROS2, you will also be able to implement each type in Python and even combine them in a mini project. Let's start. Communication is the foundation of any robotic system. Think about it. A robot is made up of sensors, controllers, and processors. All of them need to exchange information constantly to make decisions and act intelligently. That's exactly where ROS2 comes in. ROS2 makes it possible for multiple nodes to communicate with each other reliably over a network. A node is the basic building block of any ROS2 system. It's the smallest executable unit that actually does something inside your robot. Think of a node like a tiny, specialized program, one that does a single well-defined task. For example, one node might handle your camera feed, another might control your robot's wheel, and another could process sensor data or make navigation decisions. By splitting these tasks into individual nodes, ROS2 keeps your robot modular, flexible, and easier to debug. Now that we know what a node is, let's look at what a node actually looks like in Python. In ROS2, we use the RCLPY library to create and manage nodes, and every node follows the same simple structure. A ROS2 node has three main parts. First, we import the tools we need. Then we create a class that represents our node. Inside the constructor, two things happen. We give the node a name, in this case my node. We write the actual node logic, timers, publishers, subscribers, parameters, or anything else the node needs to do. Here we are just printing a message to show the node is running. Finally, we need a main function that brings everything to life. This part initializes ROS2, creates the node, spins it, meaning it stays active and responsive. And when we are done, it shuts everything down cleanly. Now let's talk about something super cool that happens behind the scenes in ROS2, node discovery. ROS2 is built on top of DDS, the Data Distribution Service, and that gives it a really powerful features. Whenever a node starts up, it automatically broadcasts its existence to the network. There is no central master, no server you have to register with, nothing like the old ROS1 master. Instead, ROS2 uses a peer-to-peer discovery system. That means every node can discover every other node on its own, completely automatically. So as soon as your nodes come online, they instantly know what topics exist, who's publishing, who's subscribing, and what services or actions are available. This makes ROS2 more reliable, more flexible, and way more scalable for real robots running across multiple machines. Nodes communicate through topics. Topic lets nodes exchange messages with each other. For example, your camera node might publish images to a topic, and another node, maybe an object detection node, subscribes to that some topic to process those images in real time. ROS2 gives us three main ways for nodes to communicate: publisher, subscriber, service and client, and action server and client. Alright, now let's dive into the communication pattern you will use the most in ROS2, the publisher-subscriber model. This is the primary communication mechanism in ROS2, and here is how it works. One node publishes data, and one or more nodes subscribe to receive that data. It's one-way, asynchronous, and it's designed for continuous data flow. Think of a topic like chatter as a shared message bus. Any node can publish messages onto that bus and any node can subscribe to listen to those messages. The really cool part is you can have multiple publishers and multiple subscribers all using the same topic at the same time. It's completely flexible. ROS2 handles all the routine automatically. And the communication is asynchronous. That means a publisher sends out data and then just keeps going. It doesn't wait for anyone to respond. Subscribers pick up the messages whenever they receive them without slowing anything down. This makes publisher-subscriber perfect for fast real-time data where you don't want anything blocking or waiting. So where is this useful? Pretty much everywhere you need fast regular updates like sensor data, camera frames, LiDAR scans, IMU readings, status updates from different parts of the robot, or robot velocity commands sent to the motion controller, and honestly any information that needs to be streamed over and over again. This model lets your robot share data efficiently without waiting for replies or blocking the system. Publishers talk, subscribers listen. Clean, simple, and super powerful. Alright, let's look at a real example of a ROS2 publisher. This is our Talker node. In this script, we start by importing the base. Then we create a class called Talker, which inherits from the ROS2 node class. Inside the constructor, a few important things happen. We give the node a name, in this case Talker. Next, we create a publisher. This publisher sends string messages on a topic called chatter with a queue size of 10. Then we create a timer that fires once every second. Every time the timer triggers, ROS calls our callback function. Here we build a string message, publish it, print it, and increase the counter. Finally, in the main function, we start ROS, create the node, and spin it so it stays alive and keeps publishing every second. Now let's look at the other side of the publisher-subscriber system, the subscriber. It listens to the exact same topic our Talker publishes on. We start with our imports, then we define a class called listener. We give the node a name, listener, and then create the subscriber. Here is what's happening. The subscriber expects string messages. It listens on the chatter topic, and every time a new message arrives, ROS calls the callback function. The queue size is 10, just like the publisher. Inside the callback, we simply print the message. Finally, the main function is exactly what you would expect. This keeps the node alive so it can continue receiving messages. Now let's move on to the second major communication pattern in ROS2, the service server client model. While topics are great for continuous data streams, services are all about synchronous two-way communication. Think of it like making a function call. Here is how it works. A client sends a request, a server receives that request, processes it, and then sends back a response. Meanwhile, the client waits for the reply before continuing. Because this pattern is blocking and predictable, it's ideal for quick, on-demand operations where you absolutely need an immediate answer. Alright, now that we know what services do, let's look at how a service is actually structured in ROS2. A service is made up of three simple parts: a name, a service definition file called the .srv file, a request message, and a response message. As you can see in this example, the top section defines the request, in this case two integers a and b. The line of dashes separates the request from response, which here is just one integer, sum. So this service simply takes two numbers, adds them together, and sends the result back. That's all a service really is, a clear request and a precise response. Now let's build a real ROS2 service, starting with the service server. This server will add two integers and return the result. We start by importing the essentials. Then we create a node called addServer. Here we create the service. The service type is add2ints. The name is add2ints, and whenever a request comes in, ROS calls our callback function. Inside the callback, we simply add the two numbers, print out the result, and return it. The main function just launches the node. And that's it. Now we have a fully functioning ROS2 service server. Now let's create the service client, the part that sends the request. Again, we start with the same imports. Then we define our client node. We connect to the service named add2ins and then we wait until the server is actually available. Once the service is ready, we prepare a request object. Finally, the main function sends a request. Once the service responds, we print the result. So together, the server performs the addition and the client asks for calculation. Now let's move on to the third major communication pattern in ROS2, the action server client model. Actions are designed for long-running tasks that take more than a split second where you want feedback while the robot works, and the ability to cancel the task if needed. Here is how it works. A client sends a goal, the action server accepts the goal and starts processing it. While it's running, the server sends feedback, progress update, percentages, distances, whatever you need. When the task finishes, the server sends a result. At any time, the client can cancel the goal. Basically, if a task takes seconds, minutes, or has multiple steps, you don't want a service and the topic isn't enough. You want an action. So now that we know what actions are used for, let's break down how an action is actually structured in ROS2. Every action is defined in a special file called action file, and it always contains three parts: the goal, result, and the feedback. And they are separated by lines of dashes. The goal describes what the client wants the robot to do. The result is what the server sends back when the task is finished, and the feedback is what the server streams while the task is running. Progress updates, percentages, distance remaining, whatever you need. This structure is what makes action perfect for long-running behaviors where you want continuous updates and full control. Now let's take a quick look at the simple action server example using the classic Fibonacci sequence. Here we define a node. This creates an action server named Fibonacci using the Fibonacci action type. And whenever a goal arrives, ROS calls our execute callback function. Inside the callback function, we start with the first two Fibonacci numbers, then build the sequence step by step. Every iteration, we calculate the next number and send feedback to the client, so the user sees progress while the action is running. Once the sequence is complete, we mark the goal as successful and return the final result. That's the entire action server. It processes long-running tasks and keeps the client updates along the way. Now let's look at the action client, which sends a goal and receives the feedback. This connects to the Fibonacci action server. When we want to send a goal, the client waits for the server, creates a goal, and sends it asynchronously, attaching a feedback callback. Every time the server sends progress, the function runs. We print the sequence as it grows. You can see the sequence being built in real time. And that's it for our ROS2 communication overview. Now you understand how nodes talk, how data flows, and how topics, services, and actions power real robotics. If you enjoyed this breakdown, don't forget to like, subscribe, and drop a comment on what you want to learn next. Thanks for watching, and I will see you in the next video.